Okay, so let's look at the eighth FRQ practice here. It says that the rate at which water flows into a drain pipe is modeled by R from 0 to 8, and the exiting rate is D, and we're starting with 30 cubic feet of water at time 0. So part A asks us how many cubic feet of water flow into the pipe over the 8-hour interval. So this is an accumulation from 0 to 8 of the R of t dt. That can simply be put into the calculator, and you're going to get approximately 76.570 cubic feet of water. All right, so let's look at part B. The amount of water in the pipe is the amount of water in the pipe increasing or decreasing at time 3. Give a reason for your answer. All right, so the increase or decrease is given by R, the rate going in, minus the rate going out, right? So if you actually calculate R of 3 minus D of 3, you're going to get approximately negative 0.313, which means that we're less than 0. So R of 3 minus D of 3 is less than 0, which means that D of 3 has to be greater than R of 3. So we're letting water out faster than water is coming in at time 3. So the amount of water at time 3 is decreasing. All right, so let's look at parts. All right, so this asks at what time from 0 to 8 is the amount of water in the pipe at a minimum. So P of t is equal to R of t minus D of t gives me the instantaneous rate of change of the amount of water that's in the pipe. So that is the thing that we want to be 0 in order to get a critical point. If you throw that in the calculator, you're going to get that the critical point happens, that's equal to 0 when t is 0, and when t is approximately 3.271-ish. So that means that my critical points here are 0, 3.271, and 0.8 and 8, right? The end of the interval. What you can do is you can actually look at the graph of P, okay? And what's happening there is P of t is clearly less than 0 on the interval 0 to 3.271, and P of t is clearly greater than 0 on the interval from 3.271 to 8. This actually should be open, that should be closed. All right, so that means that the amount of water in the pipe is decreasing on this interval and then increasing on this, which means that the amount of water is at minimum when t is 3.271 seconds. That's the absolute minimum because it's decreasing until there and increasing afterwards, which means that not only is that a local minimum, but it has to be absolute. P of 0 has to be higher than it, and so does P of 8. All right, so let's look at part D. Part D says that the pipe can hold 50 cubic feet of water before overflowing. So now we're going to look at when t is greater than 8, water continues to flow into and out of the pipe at the given rates until the pipe begins to overflow. Write, but do not solve an equation that involves one or more integrals to get to the time W when the pipe will overflow. All right, so this was problem C, this is problem D. You're starting with 30 cubic feet in the pipe. The accumulation of water in the pipe from time 0 to time W is the amount coming in minus the rate coming out, right? dt. And we want to know when does that hit 50,000 cubic feet. So that really is the equation. 30 plus the integral from 0 to W of the difference of the two rates is equal to 50,000. All right, so that's problem number 1. All right, problem 2 gives us a table of values. The V here is meters per minute, so that's going to be a derivative, right? That's a velocity. So we have Joanna's jogging, V is her velocity, and these are a sample of values from that table. Use this table to estimate V prime of 16. So that's like the acceleration at 16. So this should be, the nearest points to 16 here are 20 and 12. So you can take the V of 20 minus the V of 12 over 20 minus 12, which gets you 240 minus 200 over 8, which is 40 over 8, which is 5 meters per minute per minute. So that's going to be an acceleration. That's meters per minute squared. Use the correct units. So that's part A. Part B is use the correct units. Explain the meaning of the definite integral of 0 to 40 of the absolute value of V of t dt in the context of the problem. Approximate the value of 0 to 40 absolute value of V of t dt using right Riemann sums with 4 intervals. All right, so the first thing is that this thing is total distance, right? So this is total distance. Joanna traveled from t equals 0 to t equals 8 minutes in sorry, not 8, it's 40. 8 was last problem, right? T equals 40 minutes in meters. So it's the total distance that she traveled in meters over the first 40 minutes, right? We're going to approximate this using a right Riemann sum. All right, so that the first interval is height of 200, width of 12. The second interval is height of 240, width of 8. Third interval is height, okay, so it's absolute value. It's going to be a height of 220, width of 4, plus a height of 150 times a width of 16, which means that the total distance traveled is approximately 7,600 meters. All right, so let's take a look at part C. Okay, so now we got Bob on a bicycle. He's on the same path. He's riding for 10 minutes. This is his model. The question is, what is Bob's acceleration at time 5? So if Bob's velocity is given by b of t is equal to t cubed minus 6t squared plus 300, Bob's acceleration is going to be 3t squared minus 12t. So his acceleration at time 5 is going to be 3 times 25 minus 12 times 5, which is 75 minus 60, or 15 meters per minute. So that's going to be minutes squared. Remember, that's an acceleration. And part D is asking us what is Bob's average velocity? So B is Bob's velocity. So the average velocity is going to be 1 over 10 times the integral from 0 to 10 of his velocity, t cubed minus 6t squared plus 300 dt. Because of things, you could just simply throw that into a calculator and you're going to get 350 meters per minute. All right, so that solves problem number 2. All right, so problem number 3 gives you a differential equation. The first thing is it's asking you to create the slope field for on the grid. When I look at the scoring keys on this, basically what you're going to get is that close enough is good enough. They're not looking for perfection, but they're looking for things to be close.
I think he can. I hope Bo can hear me.
All right. So let's take this point by point. Remember that dy dt, the slope that's being represented in the slope field, is given by 2x minus y, right? So the easiest thing is to start when all of the x's are 0, which means that this has a slope of 1. This one's going to have a slope of 0. This one is going to have a slope of -1. And then this one has a slope of -2. Now, here's what we got. It's when we basically do these, we're just going to add 2 to each of these. So the slope of 1 now becomes a slope of 3. The slope of 0 becomes a slope of 2. The slope of -1 becomes a slope of 1. And the slope of -2 becomes a slope of 0. So there's a rough sketch of the slope field. It doesn't have to be any more perfect than that. The graders would be looking at just a good attempt here. So the second part says find the second derivative with respect to x and y, and then determine the concavity for quadrant 2. So given this, if I take the second derivative with y with respect to x, this is implicit, so we're going to get 2 minus dy dx. But remember, dy dx is 2x minus y. So this is going to be 2 minus 2x plus y. Now, in quadrant 2, this is x is negative and y is positive. So 2 minus 2x plus y is always greater than 0 in that quadrant, which means that I am concave up for the entire second quadrant. All right, let's look at part C of question number 3 here. And this says we have a particular solution at 2, 3. Does this have a relative minimum, maximum, or neither? So the first thing that you need to do is to check the first derivative at that point. So dy dx at 2, 3. Okay, so we're using the 2 times 2 minus 3 is 4 minus 3, which is 1, which doesn't equal 0, so we have no relative extrema here. because if we do have a relative extreme of the first derivative, it has to be 0 on a continuous function, which tells me that we are neither, right? All right, part D of this problem is a wee bit tricky and convoluted, so let's take a look at that. Okay, so we're saying that find the value of the constants m and b for which y equals mx plus b is a solution to the differential equation. So if I take y equals mx plus b, then I know that dy dx has to be m. That's not too convoluted. So this I can use with our differential equation, because this means that m has to be equal to 2x minus y. So now I have a way to relate x, y, and m. Okay, but you can play a little game here, because this also tells me that m is equal to 2x minus mx plus b. Okay, because y is equal to mx plus b. And this is where we're going to get into a little game that looks like partial fractions. M is equal to 2x minus mx plus b minus b. Let's get that there. Minus b because of the distribution, right? Which means that m is equal to 2x minus 1, or sorry, 2x let's check that. M is equal to 2 minus mx minus b, which means that 2 minus mx minus m plus b should equal 0. So I just brought the m to the other side here. So here's what's going on. The coefficient for both of these has to be 0, right? So at the end of the day here, 2 minus m must be 0 because the coefficient in front of the x has to be 0 here, which means m is 2. Aha, we have m. And here I get that m plus b has to be 0, so negative m plus b also has to be 0, which this is going to be that 2 plus b is 0, 2 plus b is 0, b is negative 2, and there is my combination. M is 2, b is negative 2. So sit with that one for a little bit. It's a little bit convoluted, but it is a pathway that gets you the value of both constants m and b given the data of the problem. All right, let's move on. Okay, so question number 4 is like one of these questions where I think they could go here because they're going to give you some information and it's just like 4 unrelated kind of questions that are all going to test different parts of the content. So the stem here is that you have f of x is equal to 1 over x squared minus kx, and then they actually work the derivative for you in terms of k. So they don't actually require you to do the derivative. So you get x squared minus kx squared. Okay. So in part A, they assign the value 3 to k. So that just makes f equal to 1 over x squared plus 3x. And then it asks to write the equation of the line tangent. So when x is 4. So f of 4 is going to be 1 over 16 minus 12, which is going to be 1 over 4. And then you also need to know f prime of 4, because you need to know the instantaneous rate of change. But we know that k is 3. So this is 3 minus 8 over 16 minus 12 squared, which is going to give me negative 5 over 16. Right? so you can write y minus y1 is equal to the slope times x minus x1, which is 3, or sorry, 4 in this problem, right? 4. So the only thing I would do is just bring the y over. And there you go. There is the line tangent to the curve at x equals 4. Okay, so the tricky bit about this problem is there's no carryover from section to section. So they change the k value, they make k 4, and they say determine whether or not f has a relative minimum, maximum, or neither at x equals 2. So the first thing you need to verify is that when I put 2 in, I have to look at the derivative, right? So if k is 4, the derivative is going to be 4 minus 4 over 4 minus, and let's see, 4 times 2 is 8 squared, right? So this is 0 over 16, right? So that's 0, so that means I passed the first derivative test for an extrema, so there's going to be an extrema there. And then we have to look at the second derivative. The second derivative here, you're going to get from the first derivative. So you're going to take low, which is x squared minus 4x, d high, right? So the derivative of the numerator is just going to be negative 2 minus high, which is 4 minus 2x, d low, which is going to give me 2 times x squared minus 4x times the derivative of the inside, which is 2x minus 4, all over low squared. So this is going to be 4 or x squared minus 4x, and it's squared squared, so it's to the 4th. Okay, so we're at a specific point here, though, right? We're at when x is 2, right? So we can throw in the 2's for the x's. So we want f double prime of 2. So this is going to give me 4 minus 8 times negative 2 minus 4 minus 4, and that's brilliant. Times 2 times 4 minus 8 times 4 minus 4, all over 4 minus 8 to the 4th. This is 0. So this comes out as 8 over, oh, that's a squared. Sorry. That needs a squared. So that's not 8. Squared, squared. Okay, so that's actually negative 4 squared is 16 times 2 is negative 32. There we go. 4 minus 8 is negative 4 to the 4th, which is going to give me 256, which becomes negative 1/8, which is less than 0. If I am less than 0, this is a local maximum. All right, so there you have it. Let's move on to part C of this problem. Part C is actually the easiest part of the problem. Find the value of k for which f has a critical point at x is equal to negative 5. So if it has a critical point when x is equal to negative 5, we want to know when is the numerator of the derivative equal to 0. So that is when is k minus 2 times negative 5 equal to 0, which is simply when is k negative 10. So that's part C. Not a big problem there. Let's get a new screen for part D because it's doing partial fraction stuff and we may need some space. Okay, so let's take a look at this. Part D, you have, oops, let's make that black because that's what you're used to seeing. All right, so part D says we're decomposing 1 over x times x minus 6, right? Because that's what x squared minus 6x is going to be. So this is going to be a over x plus b over x minus 6. You multiply through, you get 1 is a times x minus 6 plus bx. 1 is ax minus 6x, 6a, sorry, 6a plus bx. 1 is a plus b x minus 6a. So this means that negative 6a has to be 1, which a is negative 1/6. And a plus b has to be 0, so negative 1/6 plus b is 0, which means b is 1/6. So the decomposition is negative 1/6 times 1 over x plus 1/6 times 1 over x minus 6. The next part of this is to say, actually take that integral or the antiderivative. Pull out the 1/6, right? So if I pull out a 1/6, I'm going to get like 1 over x minus 6 minus 1 over x dx. This becomes 1/6 times the natural log of the absolute value of x minus 6 minus the natural log of x plus a constant, which is 1/6 times the natural log of x minus 6 over x plus a constant. And that's about as far as I would go. I don't think you need to simplify much further than that. All right, so let's look at part 5. Okay, so there is some pretty limited stuff on Taylor and Maclaurin that can be on the 2020 exam. What we're going to do here is look at this series. In part A, we're given that f is x minus 3/2 x squared plus 3x cubed plus yada 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 to negative 3 to the n minus 1 over n times x to the n, so forth and so on its interval of convergence. So it says write the first 4 non-zero terms of f prime. So f prime, the first term's 1. The second term is negative 3x. The third term is going to be 9x to the squared, which if you kind of keep following here, it's not hard to see that the next term is going to be negative 27x to the third. And it does not ask us for the general term, so we can stop there, but it does ask us for what do we get if this is as a rational function, which means that this is geometric. So we're going to go n equals 1 to infinity. The first term is 1. Each time we're multiplying by negative 3x. So that's that, which means this is 1 over 1 minus negative 3x, which is 1 over 1 plus 3x, and we're good. So that's part A of the problem. Let's look to part B. All right, so part B is running around with e to the x. This is something you should be able to recall. E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. That's the first non-zero term, 4 non-zero terms. We want us to use that in our result of the previous problem to find e to the x times f of x, and we want the third degree Taylor polynomial. So we're going to multiply 1 plus x plus that plus this times where we started here, which is x minus 3 halves x squared plus 3x cubed. And we don't need any more than that because this is, what you call it, third degree, right? So distribute the 1, gives you x minus 3 halves x squared plus 3x cubed. Distribute the x, you're going to get x squared minus 3 halves x cubed. Distribute the x squared, you're going to get x cubed over 2, right? So when we add these up, we're going to get an x. 1 minus 3 halves is negative a half x squared. 3 minus 1.5 is 1.5. Plus a half is 2 x cubed. So the third degree Taylor polynomial will be that one. All right, so that's it. That's the whole problem set. If you have questions, see me in the drop-in or drop me an email. Hopefully this is helpful.